Yeah, this is Ngao-Shield. This is the project that I've worked on. It is a project that is using the Federated Cyber Defense Grid. So imagine Kenya's digital infrastructure is currently fighting a lonely, losing war. Our defense is siloed, meaning when one agency is attacked, others remain blind to the same threat because privacy laws prevent the sharing of sensitive security logs. Ngao-Shield breaks this data deadlock by deploying Kenya's first sovereign federated grid system, which functions like a national immune system. Instead of moving private data to the central server, we use the AI to the edge, allowing institutions to collaboratively train on threats locally and share only the mathematical gradients, thereby granting every connected bank and ministries instant immunity to an attack detected anywhere in the grid without a single byte of privacy data ever leaving the building. So uh, that is what we are trying to do with the Ngao-Shield, and this is how the attack is simulated. We have an attack from the Ministry of Health. The agents at the edge creates the pattern and share it to the Nero Command Center. The Nero Command Center now is able to see the threats. Then the AI at the edges perform the analysis and creates a mathematical simulation, and then sends the system, the logs back to the system, so that we don't have, the system does not go down. So all the systems are now being protected. So this is what happens. Infection happens, then there is local learning, then segregation, where we don't use the average but we use the mediums to make sure that if an attack also sends an information, it is very rare that it would be found at the median. So when you pick the medium, that is what is being processed. And again, this one creates an immunity so that there is no other nodes become protected. Here we use the scientific backbone to make sure that this thing is reliable and that it can work. So with the AI component, autoencoders at the edge in network traffic and system behavior through unsupervised learning. So they can see the normal logs which they have trained through, and then they can see the abnormal logs. Then they perform aggregation to create the median. Then they use uh, they use the Gaussian anti-noise to make sure that the noise is detected, so that no injection ensures that individual data privacy while preserving collective intelligence. So this thing is very robust and it can be able to work on uh, low energy, or it does not require heavy infrastructure, but it requires intelligence implementation. So the architecture is that we designed the pattern where your application next, where our application now sits next to the main application. So like our Docker system is sitting next to the bank's firewall. It reads the logs the firewall produces without stopping the firewall. So Ngao-Shield operates on an unintrusive containerized sidecar, ensuring zero downtime for legacy infrastructures. And again, we don't send data and also prevent the privacy. So adding a mathematical noise randomness to the data so that specific entries cannot be distinguished. So we create the simulation of the attack, we deploy the vaccine, and then we create the summary. So these are the kind of attacks that it can prevent: DDoS, SQL injection, insider threats, and ransomware. So we are ready. It is ready to deploy because it is non-intrusive, low resource, and one click. Once the Docker is set up, it's able to run and it creates a deployment. So the next phase is we are going to see in the server how it is built, and the aspect of us is to see how everything works. So at this stage we are going to run our main server. Here is our main server. So the main server is started. It begins to receive information. This is how it runs. It performs the configuration on the edge, and then we create a user interface where the command center are able to monitor everything. The user interface works. This is how it looks like on the user side. this is the user side, and if you see the user side, this is what the user will see, or those who are managing the systems. So this is what they'll see. They see the logs, they see everything is working normally, heartbeat received, 14 completed, because the AI is learning. If you look at this other aspect, you'll see from the server that it begins to send information. It waiting for the client to be detected. So when we come to the third terminal where we send a client, here we send a client to be detected, and then when it runs, it begins to run, and then we are able to simulate everything. Here at the command center, we can see the attack now happening. So when you simulate an attack, you see everything turns red. So it see the signature mismatch, blacklist, and the model integrity is going down from 1, it goes now 0, 0.2. And then when we create another scenario, we see how this one works. And when we run another scenario, we see in that one what happens. So it works. And then when we come back to our where we are viewing from, we can see the integrity is down, which means that there is a normal traffic has been flooded. And then we could simulate the traffic. For example, this is how the traffics come from. This is the attacker, this is the attacker. Then when it goes to this node here at maybe Nairobi headquarters, then we see the Eldoret, Kisumu, and Mombasa hubs are being protected. So when you deploy the vaccine, the AI at the edge begins to learn, and then it creates an improvement. Then it begins to see the real information. It makes sure that the integrity of the system is maintained, the integrity of the logs, nothing is strange. So that it begins to rise. So that is what the system is beginning. We are able to see everything, and we are able to provide all the components that we needed to understand. So that's what makes the system very robust, and making sure that we have everything captured. So Ngao-Shield is a federated learning grid. At the edge, we run deep autoencoders inside Docker sidecars to detect anomalies locally. When an attack is detected, we compute the model gradients before transmission. We apply differential privacy to anonymize the vectors. These vectors now are sent to the central hub, which uses the coordinate-wise median aggregation to filter out malicious nodes. And to filter out malicious nodes, like in this case, the malicious nodes, and then these vectors are sent to central hub, which uses coordinate-wise medium to filter out malicious nodes and update the global model. Finally, we broadcast the update, achieving a Byzantine, robust, and collaborative immunity. So this is what makes our system outstanding.